Hello, I'm Madeleine Hoskins. In this webinar, I'm going to be talking about Intellex's new training courses, and in particular our module on System Safety Engineering and Management. Accidents on the railway have existed for pretty much as long as there have been railways. Over the years, the technology has become more sophisticated, speeds have increased, the amounts of passengers carried has climbed ever higher. Modern railways are much changed from those times. In the age of steam trains, we simply did not have to worry about things like complex software functions failing to operate as intended. System safety is all about applying techniques and processes within the design and development lifecycle to identify hazards and tease out how they might be brought about. The complexity of modern systems means that we have to be thorough and disciplined in doing this. We must then consider the risk these present and implement design changes or other strategies to reduce that where we need to. The Intellex training module on system safety is intended to provide you with the knowledge to undertake these safety tasks and understand the importance and best ways of using each technique. There are right ways and wrong ways of doing things, and we want to show you the best ways. The course will cover how safety activities are performed on projects. You will learn the theories underpinning the techniques that you'll be using. It'll cover things like the safety plan, independent safety assessment, documents, hazard and operability studies, ALAP, safety approval, safety-related application conditions, safety integrity levels, event trees, Ssenior standards, safety targets, failure modes, effects and criticality analysis, the life cycle, hazards and risks, safety cases, hazard log, common safety methods and fault trees, a whole load of things. The course is intended to provide a comprehensive set of tools and techniques embedded into the processes that are required to ensure a robust safety management system. Now, before we go on and discuss the safety module in depth, I think I owe you a little bit more of an introduction about myself. That's me in the picture there, same as me here. Firstly, though I've been in the industry a long time, I've never actually worked on steam trains like those in the first slides we saw today. I'm really not quite that old, honest. I actually started my career in the defense industry, working on radar systems, looking at reliability, built-in test functionality, and safety in an active deployment of these systems. So from early on in my career, I have been working with complex systems. I've always had a systems engineering approach, which is essential for the type of work that we do. Many of the techniques I learned then, we also apply to railway safety and RAM engineering. For example, failure modes, effects and criticality analysis, and fault tree analysis. I have developed this expertise through practical applications over the years, and I've passed this on to other RAMS practitioners through lecturing and training courses. I've worked on many infrastructure projects, assessed new rolling stock, signalling systems, power distribution, control centres. I've done this on metro and mainline railways, new and upgraded stations, depot facilities, everything to do with the railways where safety and reliability are important. This is the expertise I hope to be bringing to you in this course. Now, I want to show you how the safety module fits into the different courses that are being offered. Firstly, we have the System Assurance Appreciation course. This is a standalone 2-day course that gives an overview about RAMS systems engineering and assurance. For managers and others who would like to understand the concepts and processes involved, you'll need to pass a test as well. A CPD certificate will be awarded, Continuous Professional Development, on this course. All of our main modules can be taken individually through our online tutorials. These modules are the safety one, which I'm talking about today, RAM, reliability, availability, maintainability, system engineering, and system assurance. We envisage that these might appeal to discipline engineers and perhaps operations staff, certainly for interested RAMS engineers. There'll be online tests, of course. CPD certificates will be issued for this as well. Now, the RAMS certificate course consists of 40 hours online tutorials and supports live sessions. So it's supported by live sessions and has an exam. There will be online tests again. And then this one you'll get a certificate of the qualification. Our certificate course in RAMS and System Engineering and Assurance is a bigger course. This is a 56-hour course done again through online modules, online courses, with the addition of the supporting live sessions, which we'll be doing for you, and again an exam. This again leads to a certificate of the qualification. This is the next level up from the RAMS certificate course. And our most advanced course is the Advanced Certificate course in RAMS, System Engineering and Assurance. This builds on the certificate course content by additionally including a week-long case study, which you'll need to actually attend. It's aimed at practitioners in these disciplines. The intention is that all of these should provide recognition in the form of continuous professional development points. You'll get certificates for our 3 main courses. And we're currently agreeing with Birmingham University for their accreditation of the courses. So hopefully these will soon have full recognition from academia as well. A second, apologies. So I now want to take you through what the safety module includes in more detail. I'm going to run through these chapters only very briefly, because we don't have huge amounts of time today. But what I will do is give you just a little snapshot from the courses themselves, so you can get some of the flavour of them. Okay. The first chapter in the safety module is hazard analysis and risk acceptance. Now, safety management is essentially a process of identifying hazards, looking at their risk, determining how to reduce that risk to an acceptable level, and then making sure measures are implemented. Yet many people don't really appreciate the difference between a hazard and risk, so we carefully cover that too. Is any risk acceptable? Of course it has to be, but how much can we incorporate into our railways? How do we know when it is too much? Second chapter is System Product Safety Assessment and SIL levels. Hazards occur at the boundary of a system due to events happening within the system itself. We need to fully understand how subsystems can be systems in themselves and still lie within our top-level system. We will also look at what safety integrity levels are, how to define them, and how we can show that the required levels are being met in our designs. Next we move on to Intellex standards and common safety methods. We're going to look here at 3 main Intellex standards in a lot of detail. EN 50126, 128 and 129. Common safety methods are fully aligned to these standards, and we cover risk assessment in its own chapter. 50126 tells us how to manage safety and RAM activities, taking a systems approach over the many different phases of a project lifecycle. 128 informs us of how we should approach software, and 129 looks at signaling system requirements in more detail. Now, our chapter on safety engineering techniques is split into a number of sub-chapters, all of them quite comprehensive. The first one we have of these is hazard log management. Hazard logs work best when they are thoughtfully set up with a number of defined hazards carefully controlled. We look at how to do this, how to manage the log, and what kind of information needs to be kept in it. A hazard log is absolutely central to all safety management activities. It's not just a record. It's a tool for helping us to ensure we deal with all the many issues identified during our assessments. If the log is badly managed, then it means the safety engineering process is also being poorly managed. Failure modes, effects and criticality analysis looks at how failures go on to cause events. It's a bottom-up technique which can be applied with great versatility. We'll look at different examples like this one, performing assessments at functional and subsystem levels and applying it to interfaces and even to procedures. Next we go on to look at fault tree analysis. Fault tree analysis is a top-down technique. When we think of something that can go wrong, we look at all the combinations of events that might have caused it. We'll show you how to make your trees sensible and understandable. And we'll teach you some of the maths too. Nothing too scary. Even those who might not need to actually make a fault tree can benefit from being able to read them and understand what is going on. There are right ways and wrong ways to doing fault trees. We'll give you some guidance and, of course, a bit of practice to get the hang of them. Event tree analysis. Well, event trees consider the what happens next elements of a safety study. They help us to look at the different probabilities of things happening. They usually develop in a chronological fashion, but as we will show you, they can be applied in other ways too. Fault trees and event trees allow us to make visual representations when modeling how things are caused and how subsequently events turn out. Here's a little video clip from this chapter. We refer to our diagrams as trees because of the way that logical branches divide or come together. This is true when we're considering both fault trees and event trees. As we saw in chapter B 4.3, fault trees are a top-down technique in which we consider how a specified top event can be caused by combinations of basic events, such as system failures and associated incidents. Starting at an initiating event, event trees can then be used to look at subsequent effects and final outcomes that might arise from the undesirable event occurring. When an event tree follows on from a fault tree, the top event of the fault tree naturally becomes the initiating event of the event tree. Of course, we do not have to analyze the initiating event through fault tree analysis in order to perform event tree analysis. Event tree analysis is a separate and standalone technique. Event trees are a way to visibly show how events develop along different paths and ultimately lead to different outcomes. In essence, event trees look at how things might play out following an undesirable event, identifying final outcomes and giving us an understanding of which of these is most or least likely. I have presented an image of the event tree being the top half of an actual tree, with branches spreading outwards to a large number of outcomes. Classically, we do not work our way up when creating an event tree, but sideways, going from the initiating event on the far left to the determined outcomes on the far right. An event tree diagram models all foreseeable pathways from the initiating event and is therefore excellent for capturing and considering negative or unsafe outcomes. As you can immediately see in this simple example, an event tree is quite graphically stylized with very clear branch points. Our next chapter is on safety targets and compliance. Safety targets don't come from thin air. They must fit in with organizational, regional, national, and even international requirements. But exactly how do we do that? In this chapter, we will look at how to take the top-level safety targets and how we then apply those down to the projects. The next chapter is on risk acceptance through the common safety method. The CSM for risk assessment is a defined process to bring good practice and commonality of approach across the European Union. Even if you don't need to follow this, there are still some excellent tips for taking you through a risk assessment process. The approach forces us to carefully define what we are changing and to consider what the effects of that change might be. If we think the change is significant, and we will explain how that is determined, then a step-by-step process needs to be followed. We then look at safety cases. A safety case is a reasoned argument which is based on evidence. In this chapter, we will take you through the requirements for producing a safety case and also look at safety cost-benefit and ALAB arguments. In regards engaging an independent safety assessor and the need for safety review by statutory bodies, when we do not have anyone looking over our shoulder confirming that the right things are being done, then it is all too easy for us to start taking shortcuts, even unintentionally. Independent reviewers and safety approvers are not enemies. They are an important part of the safety process, and having them is always a benefit. Our final chapter is on the production and review of system safety deliverables. There are just so many deliverables that need to be considered. We will look at what these entail, where in the system lifecycle they need to be produced and subsequently updated. An important message of this chapter is that the safety documentation is not our principal aim. For that, we're trying to ensure that any change to the safety is done with an acceptable level of safety risk. Quiet! I have a dog in here. We should not focus on getting ticks in the boxes for our documents. Instead, we do the hard work and we record the evidence of having done so. Done professionally, the work and the documents will stand up for themselves. All in all, this module is designed to provide students with knowledge that can be applied on real projects. Overall, this module contains about 18 hours of online tutorials. We'll give you some live support sessions in small groups. That'll be online too. The online test has to be passed. The 80% pass mark will mean that you have to work hard, but it is quite doable. We're not out to trick you, just to ensure that you have absorbed and understand the information. Now, I'm going to talk a little more about the 3 courses that the safety module is actually included within. Firstly, we have the RAMS certificate course. Obviously, the safety module is a major part of this. But the other important part is the RAM module, the Reliability, Availability, Maintainability module. This has been put together by Dr. Mikkel Verma. Dr. Verma holds a doctorate degree in development of safety critical systems for railways and has over 30 years of experience in development and certification of safety systems. He's a chartered engineer of the Engineering Council in the UK. Reliability and performance is a major issue on modern railways. In this course, you will not only gain in-depth knowledge of RAM parameters, MTBF, MTTR, mean time between failures, mean time to repair, failure rates, etc., but will also be able to understand the interrelationship between them and do mathematical analysis. You will learn about RAM modeling tools like reliability block diagrams and Markov analysis, and also understand which tool is suitable for a given situation. You'll be shown how to improve reliability through better design optioneering. There will be a separate webinar on the RAM module by Dr. Verma in the near future. What I would like to stress here is that the safety engineering and management goes hand in hand with RAM. The life cycle approach applies to both, and many of the techniques used are the same. This should not be a surprise, as both the safety engineer and the RAM engineer are concerned with how things fail and what the consequences are. I often tell people that the RAM manager is the second saddest person on a project. When design engineers are getting excited about innovations and new functions, I, as a RAM person, might be shaking my head and saying, no, we have to consider how this might fail first. The saddest person is probably the safety manager, who will point out the possibilities of death or injury. So we are naturally conservative, but still get excited when we resolve a particular availability issue in design or find a practical mitigation that will greatly reduce risk. Because of the similarities, many of us work across the safety and RAM disciplines, sometimes doing both aspects of a project at the same time. So this is why the RAM certificate course is so useful. As well as the RAM certificate course, we also have two other important courses which include the safety module. The first is the full certificate course in RAM's System Engineering and Assurance. This is the next level up from the RAM certificate. It includes not only the safety module, but all the others too. Okay. So we've got the systems engineering and the system assurance and the RAM module, as well as the safety module. The certificate course, the full duration is around 56 hours of online content. There will be some online tutorials, 1.5 hour written detailed exam. You'll pass this. You just work hard. Now, there's one level higher that we have that I ran over earlier, and that is when you take all the modules together and put them together with a case study. Now, a case study is basically 40 hours of attendance to look at a practical, realistic case study of railway safety and RAMs and systems engineering. And when we put all that together, we have the contents of the advanced course. And this is the top level course that we provide. So we have all of the certificate course, so the 56 hours of that, plus 40 hours of case study, which will be live sessions attended. There will be a tutor assessment on the case study to make sure you followed and participated. So, I've reached the end of the first part of this session, this webinar. I now want to see if we can take some questions and do some answers. I'm going to just fiddle with my screen a moment to see if I can make myself a little bit bigger. Right, I think I've managed to sort that out. Now, I don't seem to have any questions at all. Any questions for me? Don't be shy. Okay. If you have any questions, please type them in on the live chat bar. Okay. Well, if no one's got any questions at the moment, I'd just like to remind you all that you can find out more information about our courses on the Intellex website. That's intellexuk.com. You'll find out all the information we've been saying today and a lot more things there. There will be other webinars coming up, in particular Mikkel Werner's one on the RAM engineering course. You can ask me any questions either through the Intellex website or through my LinkedIn account. Later on, I'll be happy to answer them for you. Okay, so what I'm going to do now is say, I hope you've very much enjoyed watching the webinar today, and hope you get some interest in the course. Have a really nice day and have a nice weekend, everybody. Okay. Oh, wait, we've got a question. Is it not that RAM engineer follows procedural route and safety engineer complies the procedural inputs? Well, first of all, I think both the RAM and safety engineers have to follow procedures. When you look at the way organizations are set up, we all have to follow the standard procedures set up for the company and for the project. I don't see a great difference between the safety engineering and the RAM engineering in terms of the procedural route. We all have to comply with the engineering procedures, the engineering processes, and we're part of the systems engineering techniques and ways of doing things. Will GSN be part of the course? No, goal structured notation is not going to be part of this course. That is actually used quite a bit in safety cases. Not so much in the rail industry at the moment, but I have seen it used. It's used an awful lot in the aviation industry. We're not intending to do goal structure notation. It's not an absolute requirement. It is a useful technique, and we may actually have a think about that. That might be something we could add in at some stage. Thank you. Any other questions? I fear sometimes that YouTube is a bit slow passing the questions on to me. Yes, we will look at SIL allocations and SIL assessments in the course, apart the systems engineering and safety requirements part. SIL allocation and SIL requirements are actually very, very important on modern railways. A lot of people get very uptight about it because the process for obtaining SIL can be very difficult, but also understanding when they need to get SIL. You find a lot of people just automatically say, oh, it's signaling system, so it's SIL 4, and control system SIL 2. There is a lot of that going on, but you need to be able to determine for yourselves exactly what SIL level your particular system function is. Okay, thank you for those questions. So yes, we'll think about goal structure notation and SIL allocation and SIL assessment definitely in the course. Okay, well, yes, that's absolutely right. A question here, all the network operators want SIL 4 for signaling system. In general, yes. And when you look at how important signal is and how it keeps trains obviously from crashing together and so on, you expect it to be a SIL 4 system. It has always been the most safety critical part of the railway, the signaling system. You can't have it there, there's going to cause problems. The interlocking must be SIL 4. Anything that does the job of the interlocking in modern software or functions, even on train control systems, you would expect to be SIL 4. However, there may be circumstances where you have other systems involved and you can get away with lowering that a little bit. So we'll be looking how to allocate the SIL levels. Okay, well, I don't want to stun you all with me sitting here in grand silence. If any other questions come in, we can always respond to them offline. Happy to do that. As I say, you can contact me and the others on the Intellex website. And also, if you want to come to my LinkedIn address, that's Madeleine Hoskins on LinkedIn, you're welcome to send me any questions there. Okay, so I'm now going to, we're at 12 o'clock, so we're at the end of our allotted time schedule. I'm going to bring this to the end. I want to thank you all for listening today. I hope you enjoyed it, and I hope you have some interest in the course. Okay, so everybody have a good day and a really, really nice weekend. Bye now.